Hello, this is Jack Jackson back again, and we're looking at um, some models to satisfy our unified geometry postulates 1 through 9. We've already seen that Euclidean geometry satisfies that, and in the last um, video we proved that our proved proposition 1 that showed that there was a minimal number of points and lines and planes that these first postulates generate. And they have to generate something, but only really so much. They could generate more, but maybe only so much, and only so much. We found that there was a model here where the set of points was just A, B, C, and D. The lines were any set of 2 of those, and the planes were any set of 3 of those. And so that's 4 points, 6 lines, and 4 planes. Now we saw that in GeoGebra. Let's review that. So here's GeoGebra. Let's go to GeoGebra Classic here, 3D view, and let me turn on the input bar down here. So I'm going to plot some points. The points we were using were 0, 0, 0, 1, 0, 0, 1 out along the x-axis, 1 out along the y, 0, 1, 0. And go out on the Z as well, 0, 0, 1. Not the only ones we could use, but there's one example. And so those were the only 4 points in there. And of course lines, there's nothing between these or anything else in the model that we were looking at before. But if these 2 points, I'll draw a little Euclidean line segment, not to indicate that those are points there, but that these 2 form the 2 points themselves are collinear. Okay, and there all your lines are just those sets of 2 points like that. And then the planes are any of the faces, any of these 3. So I'm going to do that by doing, let me see if I can find it. Use the polygon tool. There's a face. There's another face. Let's turn this around. Here's another face here. Let's give these different colors. So we'll make one of them blue. And we've got there's one. We'll make that one red. Let's see, there's a face that's down here. I don't know if I've gotten it yet. It's down in the XY plane. Let's make that face, we'll make it green, let's say. So, I don't know if I got all 4 of them, but there's 4 of these faces. Okay. Did we get this one? This one, that's an equilateral triangle. There. What color do you want that? How about light blue? Okay, so we have these 4 different faces. Do we have one right here? Let me zoom in a little bit. All right, so anyway, this is our shape here. That's blue. That one's kind of a brown color. There's the one here. It's a light blue. One here. Do we have this one? No, I don't have that one. Okay, let's make that one here. Maybe we can make that one purple. Okay, so we have the 4 faces. So anything that's in that face is in the same plane. So it's really just those 3 points. Now, what I want to do in this video is now give you a new geometry. And the new geometry is going to be this tetrahedron and the interior of this tetrahedron. So another name for this tetrahedron is a triangular prism. And we have those points. So if we take a line, let's say here, any line, this one I think is maybe in the XY plane, but we go through here and see where it intersects this surface, if not just the surface, but this whole figure. If it intersects it anywhere, we're going to find that intersection and do what that intersection is going to be is, in this case, is a line segment where the endpoints are on the surface of this tetrahedral solid. In other words, on the tetrahedron itself, and that's going to be one of our lines. So let me just do it this way, and let's pick a point. Let's do a point on the surface, on this surface, and a point on, say, this surface, and then make a line segment between them. That's a Euclidean line segment, but in our case, that's going to be a line. And so if you take any 2 points in this space that we have here, and you could always make them into a line or extend them out to be a line. In other words, there's one Euclidean line that contains them in Euclidean space, and that Euclidean line then connects here. That's going to give us one line, Euclidean line segment, but it's a line in this geometry. And so we can see that postulate is satisfied. So let's take a look at our different postulates, okay? So there's a description of the points, lines, and planes. What about the planes? Well, the planes are going to be the intersection of a tetrahedral solid with the Euclidean planes that contain at least 3 points of that solid, and we want them to be there. Now, I had to be a little careful here, and we'll see this in a minute. Okay, so the collection of all points of geometry is a set called space. So certainly those are all points. They're Euclidean points. So they're also points within this geometry. Lines and planes are geometric figures. Again, they're subsets of Euclidean lines and planes. So they're points. Sets of points. There are at least 4 distinct non-collinear, non-coplanar points. Well, one example is, once again, the vertices, the 4 vertex points. There's no line that contains all of them in our geometry, and no plane is either. Okay, let's continue on. Every plane contains at least 3 non-collinear points. That's definitely true. Again, basically it follows from the Euclidean version. Every line contains at least 2 points. Well, these are Euclidean line segments, so they have infinitely many points. Now, I was really careful here to be sure that when I defined this, I said that lines are the intersection of the tetrahedron with Euclidean lines that intersect the tetrahedron at 2 points. There are lines in the geometry that intersect the tetrahedron in 1 point, and then that intersection, of course, would be 1 point. We don't want that to be a line. If that was a line from 1 point, that would violate postulate 5, right? So I need to be careful in my definition to be very precise about that. So attention to precision like that is attention to detail is important. Given any 3 distinct non-collinear points, there's exactly 1 plane that contains it. Well, yeah, that's true, because if you've got 3 points there, there's only 1 Euclidean plane that contains them, and you take that Euclidean plane and intersect it with the tetrahedral space, and you only have the 1 plane there. Okay. 2 distinct planes intersect. Their intersection is a line. That's still going to be true. The intersection would be part of 2 Euclidean. The planes are parts of 2 Euclidean planes. The intersection is a line. That line intersected with the space will be in the 2 original planes in our space, so it will be a line as well. So this is a model now of a geometry. We've done 2 models now, 3 models of geometries that follow these postulates. The first one we can say is just that there you have just these 4 points only, and that's it. And then the lines are, any 2 of them, and the planes are any 3 of them. And the whole space is all 4. Then you had, so that was a finite geometry with just 4 points. Now this geometry has infinitely many points, but it's only a portion of the larger Euclidean three-dimensional space. So a little bit different, but still infinitely many points. If we use Euclidean distance, there's not an infinite, the lines are not infinitely long if we measure them with Euclidean distance metric. So a little different than Euclidean space. And then of course then we have Euclidean geometry as well. So we have 3 different models now of geometries that obey these first incidence postulates. Notice that there's nothing in the postulates themselves that guarantees that there are infinitely many points or anything like that, because we've certainly seen an example, at least one example, where there was just a finite number of points. But on the other hand, there's nothing in these sets of postulates that prohibits that either. So we've seen examples with infinitely many points as well. The fact that we could actually just get at least one model that satisfies all these postulates says that they are consistent.